and equivariant geometric formulas.
Well, good morning, everybody. Thank you very much, Ernesto Lupercion, the organizer, for inviting me here. I'm always happy to come to Mexico, and always happy to be in these conferences that Ernesto and his friends organize. Prior to starting, I want to announce a joint meeting that we're doing, the Colombian Mathematical Society with the Mexican Mathematical Society, in May of next year in Barranquilla. Some of you have been already there. And we expect joint sessions of different areas in mathematics. So if any of you from Mexico want to find out something about Colombia, please let me know, and we'll organize as many sessions as possible. Especially, it would be nice to have one in algebraic geometry. So Cesar and Pedro, please do something. Because the one in topology is somehow already set up. Anyway, so equivariant complex bundles, fixed points, and equivariant unitary bordism. So what I'm going to explain is some extension of what I explained a year ago in Puerto Escondido. And it's joint work with two collaborators of mine that are in Colombia, Andrés Ángel and José Manuel Gómez, one in Los Andes and one in the National University. So the setup is the following. So what I'm going to do is I'm going to get a complex vector bundle. That's somehow the original beginning, that together with an action of a Lie group, and I'm going to decompose it using fixed point sets. And this decomposition will give me a nice decomposition in equivariant K-theory, and more interestingly, will give me a nice formula for equivariant unitary bordism. That's somehow the end of the talk. So the setup is the following. I have a compact Lie group G and a normal subgroup A that is closed. What I'm going to have as a setup is I'm going to have a complex vector bundle over X, but I want that on X, the action of this normal subgroup is trivial. So what I want to understand is how a complex vector bundle that is equivariant with respect to a group behaves when I take the fixed point set of a specific group on the base, and then I see what is the fibers. So this is the setup that I'm going to study. So the fibers of these complex bundles are representations of this compact Lie group A, and of course you can split this complex vector bundle using these representations, and the idea is to study how these complex bundles behave when I take these specific representations. So this is somehow the setup. So I'll explain how is the composition. What does it give in K-theory? Then I'll explain what is the homotopy type of these universal spaces. And these universal spaces will allow me to study equivariant unitary bordism groups for specific types of families, and to somehow I'll give some nice applications of a specific conjecture that is open for many years for the equivariant unitary bordism groups. That is very classic. This is from the 70s. So again, so let me have a compact Lie group, and let me have a representation, irreducible, of the normal subgroup, and let me denote Ir of A as the set of isomorphism classes of irreducible representations, and then we can decompose any representation W of G in this way. Namely, we take these vector spaces, which are homomorphisms that are A equivariant from this irreducible to W, and we can tensor them with V, and we get simply an isomorphism that we know. But this isomorphism is as an A representation. So we want to somehow see how does this splitting behaves when we put the G. Since the G acts on the right-hand side, we want to see how G acts on the left-hand side. So G acts on the irreducible representations in this way. We simply conjugate the action, and therefore we can get what are these isotropy groups. Namely, this is the set of elements on which, when you conjugate the irreducible representation, it stays fixed and in the isomorphism class, and we will simply denote Q sub rho as this quotient. So the point is the following. So we want to somehow, as I said, I split my G representation using the sub-representations of A, and I want to see how this G somehow acts in this component. So whenever the group is fixing the isomorphism class of the representation, then as these representations are irreducible, the G, rho, and rho, therefore we should have a matrix that somehow makes isomorphism from one to the other. And what it makes is that if we have our irreducible representation, then we may extend the representation to G, but it becomes only a projective unitary representation. So what we have is that when we have this fixed point or these isotropic groups, then we may extend the representations to a projective one. And so this V sub rho becomes a G sub rho projective representation. Now, once we have this projective representation, what we will do is we get a central extension of this isotropic group that we will denote with this tilde, which is simply pulling back this diagram so that we get that this V rho is a representation of this group. It's a representation of a specific kind because the circle is acting, in this case, by multiplication of scalars, and therefore is a specific representation that we can control. Now, that's on the one side. We have the representation V sub rho. It becomes a representation of this extension. And now we can get the space of homomorphisms that respects the action of A. And it also becomes a representation of this G tilde group. The point is that in this vector space, the circle part is acting by the inverse. It's a simple formula. One can detect that it's acting by the inverse. So what we're getting is that this in the vector space, the G tilde is acting on which the circle is acting by the inverse, and on the representation we have also the representative V sub rho. G tilde is also acting, but the circle is acting by multiplication. So what we have here is in V, G tilde is acting. In this is homomorphism, G tilde is also acting. In this case, it's multiplication by the inverse the circle, and this is just the circle. Therefore, when we tensor them, the actions of this circle by multiplication and the action of this circle by the inverse cancel, and we simply get the representation of G sub rho back. So what we're having here is that this is the way to split somehow the representation of this G sub rho. One part, they both get projective, but one can control how projective they are. So therefore, one can simply reconstruct the irreducible representation by inducing the representations that we have here by these subgroups. And now we can simply know exactly how to decompose and irreduce a representation of G using the irreducible representations of A. Just one simple point. Since the connected component of the identity of the group is always inside this group, this is always a finite since I'm talking about compact Lie groups. So this formula on top is quite simple and nice. Of course, we can somehow, once we have it at the level of representations, I can put it at the level of vector bundles. So I'm going to push it to vector bundles. So what I'll do is I'm going to think now of twisted representations or projective representation of a specific kind. So if I have a central extension of a Lie group, compact Lie group, I'll denote by this group the isomorphism classes of representation of this H twiddle on which the circle is acting by multiplication of the inverse. I'm taking the inverse since, as you noticed before, I have the inverse acting. So I'll denote these groups by these letters. I put these letters so that they are exactly what will appear in the twisted K-theory groups. And with this splitting in mind, I get this simple isomorphism. It's quite a simple the representation group, say, of irreducible representations of G splits into this sum of, say, twisted representations of these specific groups. Good. Oh, that's my phone. So just as a simple example, so you can more or less see what we're doing. So let's take the 8, the dihedral group, and 8 elements. That's the symmetries of the square. So we have the group here. It has 5 irreducible representations. 4 are one-dimensional, 1 is two-dimensional. This is the two-dimensional representation, and so the representation ring of the 8 looks like this. So these are somehow the generators of this ring. And what I'll do is I'm going to take 2 specific examples to see how this representation ring splits. So the first is I take the center of the 8, which is Z2, which is generated by A squared. And so the 2 irreducible representations are just the trivial and the sign representation. the Q becomes Z2 cross Z2, and what I get is that this representation ring splits into these two objects. This one is just the representation ring of Z2 cross Z2, and this one is just the twisted representation group of Z2 cross Z2 when we get this central extension of Z2 cross Z2, which is just the H twiddle, which is simply the only central extension of Z2 cross Z2 by the circle, which is not trivial. So, and this part gets into this side here. And somehow this is the way that we're looking at it. Now, when we get C4, in this case, the irreducible representation of C4 are 4 irreducibles. The action of Z2, which is the cocurrent, is putting these two in the same class. And therefore, what I get is 3 pieces here on which I get representation ring of Z2 coming from here, representation ring of Z2 coming from here. And this one, since the action is free here, I only get 1 copy, and this is the way the splitting is getting. Anyway, so this is just at the level of representations. But one can somehow extend it at the level of equivariant complex bundles because we simply do it fiber-wise. So the setup is the same. Now we have an X, which is an H CW complex, or let's suppose just a compact H space. And then we denote by this object the isomorphism classes of vector bundles which are equivariant by this group, but on which the circle is acting on the fibers by multiplication of -1. This is just a specific bundles on which we have H is acting on the base as any action, but on the fiber the circle has to act by multiplication of the inverse. We can get the rotating ring of these objects, and this is what is called the twisted equivariant K-theory groups. So equivariant by H, twisted by this H twiddle, and this is the way to define it in general. Now, with this in hand, of course, one can just extend it to the equivariant K-theory setup, and one can split these groups in the same way as we did it in the local case, or when X is a point. And the map is very simple. We just take a complex bundle, and we just get these homomorphisms, and these become twisted bundles by these extensions. Good. Now, this construction on the left should be done at the level of universal spaces. So this is just somehow the algebraic side of it, but we should get what is the universal space here on the left and what is the universal space here on the right. And so we're going to construct these universal spaces to get the decomposition at the level of those spaces. So what we do is let us construct the universal twisted equivariant bundle of rank n. This is many notations, but UN or BUN is the Grassmannian of n-dimensional complex vector space of dimension n in the infinite one, the Grassmannian. When I put here the H means that is H equivariant. When I put here the twiddle means that the action of this H twiddle on the fibers is multiplication by -1. So how do I construct this universal space? The same way as we do it without twist and without groups. We just get all irreducible representations of H twiddle on which the circle is acting by -1. And we get infinitely many copies of them, and we put them in a vector space. This is, as I called it, like this symbol, and then we just take the Grassmannian of that. And this Grassmannian is this universal space. So that's the classifying space of vector bundles of rank n on which H is acting such that the H twiddle on the fiber is acting by multiplication of -1. Good. So this is the classifying space, and this is the universal bundle. And so what we just have is that these isomorphism classes of vector spaces is just simply the homotopy type of classes of equivariant maps from this space to this universal space. Now, the formula that I wrote down at the level of K-theory has a specific description of the level of these universal spaces. The description is what is written here. So, what is the left-hand side? The left-hand side is telling me I have here the classifying space of complex vector bundles of rank n, which are Grassmannian that I defined just before. Then I take a subgroup, which is A, and I take the fixed point set of this subgroup. And this may have many connected components, this thing in here. So what is classifying here, this thing, is a complex vector bundle, which is G equivariant, which has rank n, but on which the group A acts trivially. This is the classifying space of such things. Now, since I have a decomposition, then I could write it at the level of classifying spaces of smaller or vector bundles, because I can get these homomorphisms vector bundles. So what it's telling me is that these spaces could be written as a product. This is the induction at the level of spaces, and this is just telling me the twisted vector bundles over these subgroups. I just want to point out that this formula that you see here is exactly the same as that I want in K-theory, but at the level of the homotopy type. So, and this M here is just the induction map at the level of the induction functor at the level of space. Good. So I'll use this decomposition now to study certain properties on another equivariant homology theory, which is unitary equivariant bordism. So let me just then go there. So it was already in his original book or paper of Poincaré, on which he defined the bordism groups. This is 1898, if I'm not mistaken. And so he, in the chapter 5, he defined what is a homology. And to my knowledge, this is the first time this word was used. And if anybody knows from a previous, I would be happy to know if there is a previous place where the word homology was used. And perhaps you, Professor Griffiths, know. Where was the first appearance of the word homology? To my knowledge, is Poincaré in his analysis situs when he defined the bordism groups. So if you simply read this definition, it's just one page. He's defining when at the disjoint union of some manifolds is going to be related to the zero. And he says these manifolds, or the union of these manifolds, is related to zero whenever these manifolds are the boundary of another bigger one. This is what is written in here. And so in this way, he took the isomorphism classes of manifolds and he put a plus on them as the disjoint union, and he said, well, I'm going to split these manifolds into equivalence classes, and the equivalence classes will be called homologies. Sorry? Well, he did have a definition of manifold saying that it's the 0z of some functions on which the rank of the derivative is maximum. So that he had the definition in Rn. And this is the one he's defining as the definition of a manifold. So I don't have the previous pages, but he does have it in that sense, a series of functions. Good. So it was later on, from what I've read, that it was Noether who noticed that these things define groups, and not just like isomorphism classes of things, that they actually define groups, and it was later that these homology groups were defined. Good. So what is the somehow the pictorically is that I'm going to say that two manifolds that are embedded in some other space X are going to be homologous with the specific adjective at the end if I can find another manifold of one dimension more on which I can put the other two as the boundary. And so this is all living in a universe that is called X. And whenever I do this definition, I'll get some homology groups of X, which are the bordism groups of X. So let me just be a little bit more explicit. And I'll be using unitary bordism. Unitary means that I have some sort of complex structure somewhere. So the idea is I'm going to consider manifolds, compact G manifold. So I have a manifold on which I have a G action. And I'm going to call it unitary if its tangent bundle stably can be complexified. So you have to imagine that if I want to define bordism groups and I want to think of complex manifolds of bordism of complex manifolds, I will run into trouble because I will not have an object that has odd dimensions so that I could bound complex manifolds. So the way out is to stabilize the definition. Namely, it will be unitary if the tangent bundle plus some trivial copy could be complexified. This is the way somehow out. So they are called stably complex in some other setup. And so I'll say that a manifold is unitary if they are stably complex, the tangent bundle, but of course it has to be G equivariant. All these equations are supposed to hold in the G equivariant context. And I'll say that two unitary manifolds are cobordant whenever I find one that is dimension more, on which this happens, and this minus here means that I take the manifold M2, which has a stably complex structure, and I take the conjugate complex structure associated to M2. So this is the way to define the bordism groups. Now, whenever I take the isomorphism classes of this object, I get some set, but I could take the disjoint union, and now I get a group, and if I multiply them, I get a ring. So this is what is called I call it with omega. There are some other notations, but I'll take it as omega G on top, which means equivariant, and on bottom is a number which is telling me the dimension of the manifold I'm considering. These are called the equivariant unitary bordism groups. So as I said, these equivariant unitary bordism groups, this is thinking as a homology theory of a point. So it is a ring because you can take this disjoint union, and that's your additive structure. You can do the product of manifold, that's the ring structure. And it is, of course, a module over the bordism of the unitary bordism groups which are not equivariant. Namely, you just take a manifold with a G action and you cross it with a manifold without a G action, and you suppose that the action on the other manifold is trivial. So it becomes a module over the unitary bordism groups. And what I'm writing here is Tom's amazing theorem that tells us how to calculate these unitary bordism groups. Tom didn't do it for the complex case, he did it for the oriented or the unoriented case, on which he's telling us that a way to calculate the bordism groups of dimension n is calculating some homotopy groups of a specific spectrum, or we think it the other way, we take some stably homotopy groups of a specific Tom spaces, and these are the specific Tom spaces. Which are these Tom spaces? We just take the universal bundle of complex bundles, and we just take the Tom construction. Namely, we take the disk bundle of the vectors that are of length less or equal than 1, and we contract the sphere bundle, and these are the Tom spaces. And if we calculate the stably homotopy groups of these objects, Tom's theorem tells us that's exactly the way to calculate how many manifolds are there up to bordism. Now, it was Milnor and at the same time Novikov. You see, I've been reading about it, and there is some controversy that who did what and what did who. And so the statement as is written here, that the bordism ring, the unitary bordism ring, is a polynomial algebra on even dimensional generators, as it's written there. It's, if I understood now all the statements, is due to Novikov, as is stated here. Now, there is some paper that recently I found about Novikov, in which he explains that this statement, as it is written, it was by many people, especially Hirsebruch, told to be done by Milnor, but if you see Milnor's paper, it's never there. Somehow that he showed it that with Q coefficients that's the case, but he didn't have explicitly the generators associated to this thing. And so Novikov claims that it's his result, and there is some misunderstanding on the world that. Sorry? Well, I'm just saying. I'm just reading like 50 years later what happened. I'm reading it, and I'm like, okay, who did what? It's not that easy to really distinguish. For him, it's very important. But it's very important to write a whole page explaining what happened when and who did what. I don't know. Anyway, so whenever we tensor with the rationals, we can take these projective spaces as generators, but they are not generators whenever we put integer coefficients, and there are some specific construction that can be done to take the specific manifolds that are here, but it's not somehow a constructive thing. Anyway, so whenever we take a GCW complex, we are interested in these spaces, but what we're really interested is what exactly is the ring whenever we take the equivariant bordism groups, whenever we put a group here on top. That's the question. So what is, in this case, it's telling me what are the unitary manifolds up to bordism, but now I want to see what is the geoequivariant unitary manifolds up to bordism, namely, what are the coefficients of the theory. So this is the coefficients of the unitary bordism theory, and if I have an equivariant homology theory, the first things I need to know is what are the coefficients, namely what happens on a point. Now this was studied by Connor Floyd in the 60s, Stong and Atiyah before, and Stong, that actually wanted to calculate explicit what are these coefficients, what can we say about these coefficients. And so it turns out that it's still not known what are the coefficients for any group. So the thing is the following. So the question is, I want to understand what are these coefficients, and what I will do is I want to study these coefficients as a module over the unitary bordism ring. So as a module. And so the conjecture that it was set up in the 70s, but it was not somehow set up as a conjecture, more or less that's what it should happen. It is that the equivariant unitary bordism groups must be a free module over the unitary bordism group on even dimensional generators. Based on what? Based on what's happened, I believe, in equivariant K theory. So equivariant K theory of a point is just representations in even degrees and 0 in odd degrees. And that's somehow what would be nice to expect. That is only, that there will be only information in even dimensional generators, and also that is a free module over the other. That's what is expected. So this was studied first by Stong, 69. She showed that it holds for finite P groups. Landweber showed it in general for cyclic groups. Then Osa for any abelian group. Then Loeffler for torus groups. Then Comesania in 1996, I believe, was a student of Peter May for any abelian Lie group. And this is it. So somehow it is known for abelian groups, but the non-abelian case are is still not known. So little is known of the structure whenever the group is not abelian, and the conjecture is this one, that they should be free module over the unitary bordism groups. So I'm going to tell you an epsilon that I've done regarding the non-abelian case. So the idea is to use the only somehow tool at hand is to go back and to basically calculate the spectral sequence by hand, namely calculating the whole unitary bordism group and show it explicitly that is free. So the idea was done by Connor and Floyd, which is, well, let's just filter the unitary bordism groups by a specific isotropy type, namely not consider all types of isotropies, namely which are the subgroups that fixes a point, but control the isotropy type. And the idea is the following. So let's take a family of subgroups. This is a collection of subgroups which is closed under conjugation and under subgroup. And let's concentrate ourselves on manifolds on which the isotropy groups lie only on that set, on that family. So we are only to take into account manifolds with a specific isotropy group. Then we can also take a pair of families, one containing the other, and we may consider manifolds on which the isotropy groups of the manifold lie on the big family, and the isotropy groups of the boundary of the manifold lie on the smaller family. And this is somehow the nicest way to understand homology of pairs in some sense. It's just a manifold with certain isotropy, and on the boundary the isotropy is less. Good. So this, whenever we have a pair of families, we can fit it in a long exact sequence on which we just, a manifold with certain isotropy is also a manifold of bigger isotropy. Then we can put this one which has no boundary, then the boundary of course lies in here, and we can take the boundary and exactly we just raises one the dimension. It gives us a long exact sequence. This is the nicest long exact sequence, the original long exact sequence associated to a pair of families. Let us note that whenever we take the family of only the trivial subgroup, namely there are no isotropy groups, this exactly means that the action on the manifold is free, and therefore the equivariant unitary bordism groups of the family, which is the trivial, is exactly the same as the non-equivariant bordism groups, but of the classifying space BG. So somehow it will rely, the whole construction, on going to the bordism groups of the classifying spaces. So that's somehow the attitude or the structure. So how does one would like to construct or detect the unitary bordism groups without any restriction? Well, the idea is to take the finite group and to somehow filter it by families of subgroups on which the difference between two adjacent families is just one group. And this is the case, so we take a pair of families on which the difference is just one conjugacy class of subgroups. And in this case, you want to take a manifold which has isotropies here, and in the boundary is just all the subgroups in here besides one. One can take this manifold and localize it in the fixed point sets of that subgroup, look at the normal bundle, and the normal bundle may be classified. So the idea is, I take a manifold which has certain isotropy. Oh, let me just give it in an example. I'll put it in a drawing, and then I'll go back. So this drawing is telling me that the group I'm thinking about is the symmetric group in 3 letters. The subgroup I'm thinking is the group generated by the letter B is Z2. And I have here a bordism, 2-dimensional bordism, or a manifold 2-dimensional on which it has fixed points of the whole group. But if you see the boundary, in this case, has no fixed points. So this is an object in the bordism group of all subgroups, comma, in this case, for example, the trivial subgroup. And so what I'm doing is, if I have such a family, I may localize it in the fixed point sets of the subgroup I'm thinking about, say the difference of the families, and I may take the normal bundle of these fixed point sets, which becomes, as we see, the normal bundle, we have representations of this group, but the only representation that doesn't appear is the trivial one, because that's why the action, the action is free whenever the action is trivial. And we may contract all these other boundaries of the manifold to the boundary of this normal bundle. So that's somehow the way to go from a manifold with boundary to an information of the normal bundles. So this manifold that lives in here, so this manifold is an element of the second bordism group, equivariant by the symmetric group with respect to these 2 families that I wrote in here. I could send it to what? I could send it to take the fixed point sets of the subgroup, which is these 2 points in this case. But these 2 points have a normal bundle. The normal bundle is a complex 1-dimensional bundle, which is classified by BU1. This BU1 is recalling that the action of Z2 on the normal bundle is given by -1. And I just send this object to this map, which is an element of the 0 bordism group of BU1. So this is how, going back, I take a manifold, I take the fixed point set of these objects, of these manifolds, but they have a normal bundle. So since they have a normal bundle, the normal bundle is classified by these things, since I said how these complex bundles get split. And because the action is of this type, the action of the reduced group is free. So what I have here is a bordism groups of some classifying spaces, which are Grassmannians of some kind, on which this group is acting, and the action, I need to make it free, so I could, a priori or in principle, I could calculate these things. I could. Nevertheless, I cannot. Well, I'm not able to do it because these twisted Grassmannians equivariantly are highly complicated. I haven't been able to calculate them. But in certain cases, one can. And somehow, as I just said before, all the abelian groups are calculated in the abelian groups. Why is easy to calculate these things in the abelian groups? Because all representations are one-dimensional. So all these classifying spaces become generated by these one-dimensional representations. But whenever we have a group that is not abelian, we have representations which are not one-dimensional, and then the Grassmannians are very complicated. So with my collaborators and mine, we have been able to go one epsilon, and we now have the dihedral groups, but not any dihedral groups, only dihedral groups on which the cyclic part is coprime with 2. Because in the case that if the cyclic group is not coprime, let's say, for example, the dihedral group on which this is of order 2 and everything here is of order 2, so, or this is Z2 acting on Z4, because the prime is the same in both sides, our calculations don't work. So we have been able to do the dihedral groups, and we expect that one can move a little bit forward this question, and this is what we're doing. Of course, this is an approach that is, as far as I can see, it's impossible that it will reach a place on which one can say for any finite group, the equivariant unitary bordism groups are a free module over the other ones, because it's very constructive. Take it case by case. Take a group, split it, take a specific families, take a specific fixed points, look at the Grassmannians, and I don't know if this method will somehow show that the conjecture is true or false, whichever case, but at least one can go and take another groups which are constructed by cyclic groups acting on abelian groups or these kinds, but so far. And the complication lies on the calculation of the homotopy type of these Grassmannians. So the twisted Grassmannians are so far not calculated. These are some sort of projective Grassmannians, and not even the homology or cohomology are calculated in the equivariant setup. So somehow the tools are not there to calculate, and it's difficult but very interesting. So thank you very much for your attention.
It seems that the technique you're using could be also useful for solvable groups.
That is true. That's what I had a proof for the solvable group case until next day, which I showed it was false. It might think, because one has the cyclic group here and one can by induction. But first of all, as long as the cyclic group here has not coprime number with the group on the left hand side, the kernel, the homology calculations become difficult, very difficult, because I need to calculate some spectral sequences, and I don't have the arguments. I somehow believe that whenever they are coprime, yes. So I assume that the kernel, I have the conjecture, and I put the cyclic group here, and I just construct it. But I need to do it group by group. I need to build it up, and I haven't been somehow able to do it. But I suppose, yes, solvable is the case that I would expect it would fall, hopefully. Omega star BG. Omega star BG is a module over a polynomial ring in even dimensional generators. That's the only thing I know. I want to prove that it's free. It could have a lot of torsion. It could be as horrible as possible, but we expect not. As I said, the idea is that if I have K-theory, equivariant K-theory is representations, and it's a module over the integers. It's a free module. But it's just out of, I hope, because one has to simply calculate that there is no manifold that is torsion in this setup. Could you repeat what the twisted Grassmannian is, the classifying space? Well, it's just a funny name for a Grossmanian. So the twisted Grossmanian is just, where did I put it? It is this. So it's, as a complex vector space, is just an infinite dimensional complex vector space. That's it. So just take the Grossmanian, but it has an action. The action is of this group H twiddle, on which the circle is acting by scalars. So it's put only by scalars. Now, when you take the Grossmanian, since the circle is acting by multiplication, the circle action on the Grossmanian is trivial, because if you take a vector space and multiply by a circle, is the same vector space. So then the action boils down to an action of the group H. But on the fiber is acting strangely. So as a Grossmanian without the group is just BUN. So the homotopy type that is not equivariant is BUN, but is as an H space is what is complicated.
That's right, but then that allows you to define term class or some characteristic classes of those bundles, and you can call it.
You're right. You say take the cohomology of that and pull them back, but I don't know what is the cohomology of that. So you say so. The question is, what is the homotopy type of these objects? That's the question. So if I can do it, then I can pull the information back, and you can do it homotopically or algebraically or whichever method you want. They are equivalent, but the one you may to be able to distinguish something of this object.
Any other questions?
Thank you very much.
No puedes usar lo que hace Andrés Ángel de